Professor David Castañón and François Zayek. We are very pleased to say that Astrophysics has been funding this research directly for the last 7 years and has been working closely with Professor Castañón and his team for the last 4. Their bios are on the invitation page. There is a link to the bios for more detailed information. I refer you to that. And with that, hand it over to David and Francois.
Good morning, everybody. So this is the title that we're going to speak of today. Let me just briefly just move on to the presentation and highlight that, first of all, this work was sponsored by Astrophysics and by ALERT as part of the Center of Excellence work, and it involved many more people than the two of us. Many thanks to all the participants, all the engineers involved on both sides, the students that supported this. But I want to specifically acknowledge Fernando Quivera, who started working with us as a graduate student and has continued working with us after graduation. And he's an integral part of developing and implementing many of the algorithms and approaches that we'll be discussing today. So first of all, let's talk a little bit about the problem of interest. We're trying to do CT inspection of skids, air cargo skids. And Astrophysics designed the multi-view CT air cargo scanner instrument, a dual energy imager that can collect multiple radiographic projections. And in addition to that, do a volumetric reconstruction along the way. This sketch that you see here gives you an idea of the dimensions of the machine forever, but what you see is, you have a belt where the conveyor belt can go forward and the exit lane on the far side, and the dimensions are such that you can take a relatively large cargo skid into them. More important to us is what goes on in the next slide, which is, okay, so how do you actually collect imagery right there? So on the top of this illustration, what you see in the blue are basically, blades of detectors, both along the side and along the top. And there'll be a source somewhere around belt height on this area that will be providing illumination on those detectors. Let me go to the next slide and give a slightly more detailed idea of what this looks like. So single source, as the object of interest moves along the belt, it intersects basically fan beams that are going towards blades of detectors that go up along the side and along the top of the detector, so therefore collecting a projection. As it moves along on a forward pass completely, each of the projections will collect the equivalent of a radiograph, the equivalent of an AT system, a two-dimensional projection of a slice of the object of the object as it goes through. What happens at the end of a pass is there's a rotating stage that the object can be rotated by a variable number of degrees, and then a reverse pass can be sent through. And as the object goes through, you collect different radiographic projections of the object along the way. A third pass can go through, etc. And each of the passes collects radiographic projections. The projections are sparse angles. There are gaps between the projection angles here, and there are also gaps created by the rotation. But nevertheless, that's the data that we were presented with initially as a challenge of saying, okay, can we do something effective for being able to reconstruct the volumetric information inside of these projections? Let me go to the next slide and show you a little bit what some of those projections are. What you see here is basically a set of shelves with some objects both at the very bottom shelf and at the top shelf. And these are 6 of the possible projections that you see as the objects pass through the detectors. You see a little bit of distortion at the top because of the detectors that are slowly numbered are the ones along the top of the machine. The other ones are along the back of the machine. So there's a little bit of a L-shaped type of distortion that you'll see. But nevertheless, this is the raw data that you can collect of projection images that look like this. The projection images are very valuable to start with to an operator. You can see that they can immediately start focusing on areas of interest, but providing additional volumetric information for crowded images is also very important, which is a challenge that we were trying to address in our task. So because of the sparse volumetric reconstruction, we were looking to apply techniques that were different from standard filter back projection techniques. The irregular sampling associated with that made the direct filter back projection ideas hard to apply. In addition, unlike standard circular CT scanners, we weren't able to do slice by slice type of imaging because of the radiation. So this forced us to look at a fully volumetric reconstruction at one time, where instead of looking at multiple slices we could isolate, we're trying to partition and reconstruct the entire volume. This led us with inverse problems with a large number of unknowns, which I'm just highlighting a little bit the order of magnitude of the problem that we had in mind in this context. So we quickly tried to explore techniques, algebraic techniques for iterative reconstruction that exploited the models of where the sensor and the source were being located. So without going into great detail, a lot of the iterative reconstruction techniques are posed as what we call maximal posteriori reconstruction, using some form of regularization technique that we see here, and something that relates to the distribution of the measurements given a hypothetical image that we were trying to inverse. And we were posting it as an optimization problem. And of course, this is just basically at the beginning of the problem. We therefore had to find good algorithms to solve this problem, and this is something that was always a challenge for us. Our iterative algorithms are going to work in the obvious way. We start with all the measured data, the projections that you saw on the previous slide. We will guess images inside of them and predict the measured data from those images using forward projection techniques. The comparison with the measured data will generate errors, and then we will then compute corrections to the estimate, using back projection type techniques to update the image. This loop obviously has to run several times to get a good quality image out of this. But the biggest issue is that this highlights where the primary computations come in for us. We begin with a lot of measured data. As we highlight, all of the projections together have to be processed simultaneously. We have an initial image that's relatively large. We have to compute a forward projection of that image to predict the measurements, and we have to compute corrections to each of the voxels in the image in this context. These two blocks in the diagonal are the primary things that we have to design in our algorithm. So let's go a little bit to the next part. First of all, a model. We looked at a model that's a typical statistical measurement. We're measuring in photon counts using a typical Beer-Lambert law. We tend to assume that our models are Poisson distributed with rates that are proportional to some background flux in addition to source flux and an attenuation element where AI is typically the line integral for the detector for measurement I. And this particular I is indexed by detector, and it depends a lot on the position of the specific where on the belt was this measurement taken, the timing of the belt, and the particular detector on whichever blade we were reading it from. In this context is what goes into I in this context. So back to where I was. So we have a resulting, if we were to now write equations to what we had before, the resulting optimization problem is highlighted for you down here. We're basically minimizing over a non-negative attenuation for each of the energies that we're dealing with. We do this at both the low and the high energy spectra. Something that relates to the attenuation prediction with the error. This is a log likelihood part, and a regularization term with some directionality where this is basically a penalty that tries to make sure that we smooth out the regions that we're trying to reconstruct in this context. The big problem, this looks interesting and nice. There's a couple things to highlight. Big N is 10 to the 8th. So there are many, many unknowns in this context, many measurements. And the things that we're inverting for in this context, the things that go into the field mu, is also of that general magnitude, very large set of variables in this context. And the other thing is fundamentally that these projection matrices, as you know, in tomography, they tend to be non-local. These are not operators that are just working on one piece of data at a time. They're collecting elements of the field along a full line integral, which can be significant in terms of numbers of elements, but they're sparse in this context. So the first thing we have to do is look for algorithms that, in my opinion, would provide us with a very high degree of parallelism for allowing us to execute almost all the iterations in parallel. And in addition, we were interested in pipelining the data processing with data collection, because for every pass, you can imagine that some of the data is available earlier, but that doesn't allow us to necessarily reconstruct the slice. So we need to figure out techniques that allow us to process the data in a pipeline way. This led to some of our initial focuses on what did we look for in algorithms. And the algorithms that we started with and we choose is something called a separable paraboloidal surrogates. It's developed near the year 2000 by Jeff Fessler at Michigan, as a PhD student at the time. But the principle, it uses a couple of interesting principles. The first principle is the idea of surrogate optimization. In surrogate optimization, I've illustrated it in this diagram, we have a function that we might be trying to maximize. If we can come up with another function that is a lower bound to that function, but touches it at a particular guess where we're at now, but it's much easier to maximize, then we can, if we maximize that lower function, then we make progress towards the maximum of the real function. And so the idea of a surrogate optimization is to make sure you get a lower bound if you're maximizing, or an upper bound if you're minimizing, to the function that you're trying to optimize, and then make sure that you do it in a manner that's easy. Now, that latter part is loaded. What do we mean by easy? Well, it'd be great if it were quadratic, because we know that we can maximize quadratics in one step if we had the function for quadratic. It'd be great if it were a separable quadratic, that is a function where there were no cross terms between variable 1 and variable 2 or any pair of variables, because then you can maximize each quadratic independently and know the optimal step size without necessarily doing this. This plays into the theme of how do we get a really high degree of parallelism for executing the algorithm. And so what we literally do is at every time we have a guess to our function, we compute a bound based on separable quadratic functions at that point. That is tangential to that, they're quadratic. Therefore, each of them can be optimized in closed form in a single step. And it allows us, and in parallel, with no interaction between them. This is in contrast with computing gradients or other techniques that may require computing a lot more coupling in the solution that would be slower. So I said, this allows us voxel by voxel optimization in closed form. And they're guarantees of convergence to the global maximum, theoretical guarantees, but in practice, it's also a question of how well does it work in practice. So what do the computations look like now? So we start with a guess at the field we're trying to reconstruct. For every possible measurement, for every detector object position that we collect, we can compute the line integral of that predicted field measurement using the tomographic operator that we described. We can then predict the value of the measurement associated with it. And the only thing that's unusual here is that this particular line integral, we compute that geometry directly on the fly in parallel for every thread. It's much cheaper to actually do the online computations than to store them in this context. So the slow part of this is collecting the data from the volumetric reconstruction and providing it to each of the projections that you're dealing with in parallel. Then the update. For every voxel, the update field can be done by literally computing the solution of each quadratic in parallel. And this is just a brief outline of what the computations look like. Again, it's very data parallel because of the design of the algorithm that we've chosen, but there's a little bit of irregular data access because every voxel that you're trying to update has to get the errors from every potential measurement that would intersect that voxel and able to compute that. This is the back projection step. The irregular data movement make it slower, and we've worked a lot to get that to be faster. Pipelining of computations was also another thing that we were interested in doing. And the approach that we took is something that's known in the field as ordered subsets, which is that you can begin the iterations by using subsets of the measurements from each pass without necessarily waiting for all the passes to be completed. The image reconstructed for intermediate measurements can be refined as you collect measurements from subsequent passes and you refine them. And so we use those in that approach in this context. There are two advantages to this. Number one is that each of these computations uses less measurements, so it's a simpler forward projection technique. And it's less data transfer and less memory required for this. It required an interesting design in how do you organize the iterations, how do you wait for the process to go through in this context. So now we going towards real time. We're shooting towards data parallel implementation. We chose a target GPU in the NVIDIA family. It's a gaming type of GPU. The number of CUDA cores tells us a little bit of how many parallel computations we can execute at the same time in this context. And so we implemented this in CUDA for projection, divided the measurements into blocks of threads. Each measurement, as it computes its own projection row AI, accesses the values that it needs to predict measurements. The back projection recomputes the column elements of the same matrix. And again, it's sort of unusual to recompute a lot, but as you learn more in parallel processing, repeating computations is much more efficient than getting them in and out of memory. So let me illustrate how this works. So this is an example where we basically tell you how much it works. We're taking a voxel, approximately this many voxels in dual energy, using 2 GPUs. You can imagine in this context, it takes us about 5.5 seconds to do the whole processing from scratch. This is the image that you saw before. You saw the projections. This is the volumetric reconstruction that we tend to get for that. And you can see that this is basically provided as an augmented view, a 3D, where the operator can slice into or zoom into any regions that they want to. And it provides the depth information that's not typically present and not obvious from the projections all the time. Well, obviously will help us identify the materials that are more interesting. Notice in here, we've also corrected for all the distortions associated with the bent detectors that you might have seen in the projections along the way. So we're working on a few extensions that are interesting here. We're trying to improve the memory management on the GPUs in this context. We're also looking at some techniques for improving regularization approaches to getting sharper edges and contrast in this context and translating those into parallel implementations. And we're also exploring basis decomposition techniques for reconstruction of coefficient images such as photoelectric and Compton and being able to integrate that directly. We have already designed Fourier parallel decomposition algorithms for this, and they've introduced small overhead over the versions that we've shown so far. So basically, I just want to conclude before passing it on to François and telling you that it wasn't easy to translate university research into commercial environments in this context. The experimental data often differs from some of the assumptions that you like to have. And a lot of what we had to do was make some judgments, system engineering trade-offs, to trade off speed and accuracy to make sure that whatever clever solution we came up with is something that would also meet the real-time requirements of the instrument. But it did present us a great opportunity to translate some of the basic concepts we were doing for multispectral sparse CT imaging towards an important application. And just want to highlight that our collaboration continues because frankly, every time we come up with something that appears to work, more problems emerge and say, well, why don't you get it to do something new? And these new directions continue to give requirements, particularly when you start interacting with customers that, well, wouldn't it be nice if we also had this? And at this point, let me pass it on to François, who will augment the comments that we've made.
Thank you, David. That's exactly true. Listen, my part of the presentation really is strictly from the commercial angle. So what happened is where David left with the 2 GPUs, we are implementing those dual GPU. They are NVIDIA TI 2080, and commercially they have extremely moderate costs. So for us to be able to use it, we have to make sure we maintain our costs as well. With those dual GPUs, we are reconstructing the images the way that David has described and at the resolution that David has mentioned. And we, after many, many palettes that we have scanned, our reconstruction time has always been around the 5.6 seconds. So what we have done is we have now moved to the higher resolution platform. So we are now operating at a resolution similar to that of checked bags. And with that new resolution, we have brought in new problems to the table. One of them is the size of the unknowns, the way David explained it, or at least the size of the files. Keep in mind, we are working with two files, one for the high energy and one for the low energy. And each file is in the multiple gigabytes of size. So their size is quite large. So as we brought that problem to the table, we ran into the reconstruction time issue. And then we ran into another problem we did not really know about first, is running out of memory. So the GPUs were saturated in memory. So our collaborative work with Alert, they really succeeded in maintaining the same GPUs and restructure their memories in such that they can reconstruct the new images that are equivalent to the image resolution, equivalent to that of checked bag, but yet we're imaging the full skid at that resolution, and knowing that the transmission images, all 35 views of the transmission images are taken at a millimeter resolution. So it is equivalent to that of the carry-on bags. So we have achieved those. Of course, we lost a little bit in speed or in reconstruction time, but where that took us is much better images. Now, our continuing work with Alert, whether NEU and BU, our continuing work with Alert has led to faster reconstruction time than what you see here. And then with those faster reconstruction time and the 2 millimeter or the checked bag equivalent resolution, as the skid finishes scanning, and by the time it is exiting the tunnel, we have the image already, the CT image already appearing to the inspector. So we are working in almost pseudo real time. I will stop here. I want to thank, again, I want to really, the continuing of our efforts with Alert has been extremely successful. And I want to thank the teams, the Alert teams for their efforts working with us. And I would stop here. Thank you.
Thank you, David and Francois, for this wonderful presentation. We do have a couple of questions. The first question is, can this technique be applied to larger cargo containers?
I see no reason why that would be that would be a limit. But you have to choose your resolution. So the question becomes one of, do you want to image at the checked baggage resolution for a larger cargo container? The particular, we didn't talk about the energy spectra of the machine, and if for the larger containers, you may also want to focus a little bit on choosing the energy of the source to make sure you get sufficient penetration. But mathematically, there's no reason initially to think that the technique would not work.
All right. The next question is, what were the challenges in creating an effective university and industry collaboration?
Interesting. Would you like to take that?
From our perspective, if we put in a problem on the table that we like to resolve, and we see that we are moving toward that solution, and that solution is quite effective, there is absolutely no reason not to continue. And our work with an EU or with BU has been very effective. And really, I lay down the problem exactly as it is. I tell them exactly what are my issues, and we present what our target is in order to commercialize the part, and we work jointly, and it has been very successful so far.
Nice. The next question is, typically, how many iterations are needed for reconstruction? What is the stopping criterion?
That's a bit of a question that, frankly, we're still working on, but the reason is the following, that we do some iterations while we're still collecting data. And you can look upon those as anticipatory iterations rather than the final iterations in some sense. If we had just to say, let's process all the data at the end, wait, batch it, and take the delay time all the way through, we would say that it would take us maybe 10 iterations of the main algorithm. Of course, each iteration is doing 10 to the 8th projections at the time and corrections, but about 10 iterations is sufficient for us to get a high quality image. With pipelining, we can get that down to the number of iterations after you finish collecting the last data to very few iterations.
All right. The next question is about how many angles or measurements were used in the image of the shelves?
In that particular image that you saw, that reconstruction was using 30 projections.
Mm.
Actually, yeah, I believe, yeah, 30.
All right. And our last question is currently, what is the benchmark for the speed at which other instruments scan air cargo containers?
I'll leave that to Francois, perhaps. You have
Yeah, CT imaging, I don't know if there is any other product. I am aware of another product being developed, but there is no benchmark to compare to anybody else. But you can imagine you are imaging a complete skid in 5 seconds after you finish scanning the skid. That is an outstanding schedule timing.
All right. That's all the questions that we have for today. Thank you again, Francois and David, for this wonderful talk. And thank you, everyone, for joining today. And I hope you guys have a great rest of the Wednesday.
Thank you.
Thank you.
Okay.
Thank you.